Good morning, students. Today I am going to give a thought about rings and integral domain. Means final year paper 1, 3.1 paper. So, so the first algebra, rings and integral domain. Means simply as a rings and integral domain. See, the students are familiar about the groups. What's a group? Group is a single operations. See, the group operations we all are familiar. Closure, associative, identity, and inverse. Closure property, associative property, identity, and inverse. So here, suppose if we take a plus, if we sum of the two elements, sum in the group, also identity is there, inverse is there. If associative like that. So we are familiar regarding that operations, either additions, either multiplications. Only one operation at a time, student, group operations. So you come to these chapters and rings properties, the students are able to understand the difference between the groups and rings. Students can learn the definitions of rings, fields, integral domain, and ideal, and able to solve the problems on ideals. This is the regards in the object of these sessions. So we may not. Suppose if we take a group, suppose I take a Z file. What is Z file? Set of all 0, 1, 2, 3, 4. So I take a operations under additions. Operation under additions 0, 1, 2, 3, 4. 0, 1, 2, 3, 4. So we get here. If we suppose if we take 3, 4. What's a 3 plus 4 is 7. 7 can be written as 2 because see 7 divisible by 5. What's the remainder we get? 2. The remainder is 2 like that. And the residue class modulo n means residue class modulo n. Similarly 2 plus 4. 2 plus 4 is 6. 6 can be written 1. Similarly 2 plus 5. 2 plus 3. What's the 2 plus 3 is 5. 5 can be written 0 means residue class modulo n. That is a property you are using. You write here remainder. If we get more than that, if we in the set then if a 5 more than 5 we get divisible by 5, the remainder we get the set means closure property is over additive, identity, and inverse. So we are this is our familiar about in the previous semester, whatever in the previous classes. So yeah, using this property you will extend that properties. Group were studied in the previous semester, and definition of group involves a single binary operations. We know that there are two binary operations, namely additions and multiplications. By using the same operations, we used simultaneously using additions and multiplications. Not only simultaneously, suppose both the condition is exist here. Both the condition is exist here. So by using this ring there, sum of a two element is an again element. Product of an element is an again elements. Whatever regarding the field. Suppose set of all integer. If you take a set of all integer, sum of a two integer, again an integer, product of an integer. Come today in the set of all natural numbers. Suppose if you take a natural number, what is the set of all natural number? 1, 2, 3, etc. etc. See 1 plus 2 again a 3, 3 plus 5 again 8. Again I take a 3 into 5 again a 15. 15 belongs to n. 8 belongs to n. S. And product and additions belongs to set of all n. But in the set n, 0 does not fold. Also division does not fold. Subtraction does not fold. Suppose 1 minus 3. What's 1 minus 3? You get minus 2. But minus 2 does not fold in n. But 1 is there, 2 is there. 1 by 2 does not fold in n. This is saying some binary operation does not fold in the set of all a natural number. Some only addition and multiplication is fold. Set of binary operations, only two binary addition and multiplication. On the number system, such an integer, a rational, a real, or complex number, with respect to additions, they form a group. Also, the non-zero rational, real or complex number form a group for multiplication. Many of the properties of numbers depend simultaneously on the both operation of addition and multiplication. This is a point to be noted. Many of the property of a number depend simultaneously on the both operation of addition and multiplications. This is addition, simultaneously addition and multiplications. The two operations are interrelated. The two operations are interrelated. This leads us to the study of algebraic system with two binary operations. In this chapter, we shall study one such algebraic system. It has two binary operations subject to axioms similar to properties satisfied by addition and multiplication in Z. Such an algebraic system will be called a ring. So, yeah, I'm using the satisfied addition and multiplications. Yeah, now only I told now. Suppose sum of a two integer is an integer, product of an integer is a integer. So simultaneously using addition and multiplications. Addition and multiplication again belongs to that set. Again belongs to that field, either Z, either N, set of all natural number, set of all a real number, set of all a rational number, set of all a complex form. So simultaneously word additions and multiplication. Such an algebraic system will be called a ring. Now, students are able to solve the problems on rings and field. This is applicable for higher studies. If you go for higher level MSc, so in a MSc field, we go for extensions of algebra. Extensions of suppose you give Lie algebra, then some already Lie algebra, some specialization of algebra, Boolean algebra, and also we know the Galois extensions field. This is very applicable in Galois extensions field, like that. So other higher courses, applications, methods is very useful in the field of computer science, like a Boolean algebra, chemistry. Students will be able to understand the difference between the groups and the rings. Student can learn the definition of rings, fields, integral domain, ideals, and able to solve problems on ideals. See, this is the next we go for what's the ring field, regarding rings field, what's the integral domains, what's ideal, to solve the problems on ideals. This is the problem. See, this is before, after that, what is the properties regarding the group and the ring. Let me come to the definitions of a ring. Let R be a non-empty set. Let we take R to denote a ring. Capital R, we denote a ring, not essence. A non-empty set. Equipped simultaneously traced operations. Equipped with two binary operations called addition and multiplication, and denoted by additions plus and multiplication denoted by dot. Some textbook instead of dot using a star. Some textbook instead of dot using a star respectively. Suppose if you take a two element, if R is a non-empty, choose at least a two element in a ring R. A and B belongs to R. A and B belongs to R. Sum A plus B in R. The product AB in R. Then the algebraic structure R under addition and multiplications is a ring. And algebraic structure addition and multiplication is a ring. See, we are familiar. If you take A plus B equal to B plus A, this is called abelian, or simply as a commutative. A plus B equal to B plus C. See, 3 plus 4 equal to 4 plus C. Some should be equal. The same way. So, if we take a three elements, A, B, C belongs to R. Addition is associative. A plus B, R plus C equal to A plus R, B plus C. So, if we take any three elements, some should be the same. So, addition is a commutative. A plus B equal to B plus A. For all A comma B belongs to R. Now, you come to that, there exists an element 0 in R. There exists an element. See, if R 0 in R, suddenly we can add 0 plus sometimes we get an element. So, there exists an element 0 in R such that 0 plus A equal to A for all A belongs to R. See, 0 in R, if we add any elements, 0 times of that, 0 term plus times of that, we get an elements. That is 0 plus A equal to A for all A belongs to R. See, much more. How we get an element 0 in R? Suppose we take element A in R. So, minus A is also in R. If we add additions, binary operation addition, A plus of minus A is equal to minus A plus of A. You get a 0. So, 0 when you are in a group, we get identity element 0. So, something we are adding element, we get a 0. The element that times of that is suddenly as the inverse of that elements. Suppose I am taking A plus of minus A plus of minus A equal minus A is the inverse of A. Simply I say that is in the group of A. To each element A in R, there exists element minus A in R such that A plus of minus A equal to 0. So these are all regarding under additions. This property regarding under addition. You come to the multiplication is associative. That is A of BC equal to AB of C. This is a multiplicative under associative for all ABC belongs to R. Multiplication is distributive. For suppose if you take A of B plus C equal to A into B plus A into C. This is you are multiplying elements in the left hand side. Multiplying elements in the left hand side. That is called a left distributive. Again, B plus C of A equal to B into A plus C into A. That is called a right distributive. You are multiplying an element in the right hand side. That is called right distributive. These are all simple property regarding rings. This property word in a ring. That is called a ring or structure, algebraic structure under additions, under multiplication. This is word in any ring, word in a ring, that is called a ring. So we come to the what are properties, elementary properties of a ring. Suppose if you take, let all if a ring for all A comma B, the ABC belongs to R if you take elements. So, if you take A into 0, first property, 0 into A equal to 0. So, we are proving this theorem simple. We using any two operations here only. Using a two operations. So, using a two operation, we use A into 0, A of 0 plus 0. Instead of 0, we can write 0 plus 0. Here, I am using only two property. Simultaneous property, addition and multiplication. Instead of 0 can be written 0 plus 0. So, A into 0 plus A into 0. A into 0 plus A into 0. So, in the left hand side, simply A into 0 is there. So, add 0 plus A times of 0 is equal to A into 0 plus A into 0. So, here cancellation law is followed. Right cancellation law. A into 0 one times, A into 0 one time get cancelled. Suddenly 0 is equal to A times of 0. Similarly, A equal to 0. This is simple property, but I am not giving but simple explanations by using only two operations, addition and multiplication. Yeah, I am using a distributive. Regardless, see A into 0, we can write A of 0 plus 0. A 0 plus 0, A into 0 plus A into 0. So here left hand side A into 0 is there. 0 plus A into 0. A into 0 plus A into 0. So right cancellations is for A into 0, A into 0 get cancelled. 0 is equal to A into 0. Simply say A equal to 0. Simple. Only you are using distributive property, addition under distributive property under additions. We come to the second elementary property, A of minus B. What is A of minus B? We can write C is equal to minus of AB is equal to minus A of B. So we are Instead of by above conditions, a of minus b plus b. What is minus b plus b? 0. 0 can be a into 0 we know, but the first property a into 0. So instead of 0 we can write a of minus b plus b. Minus b plus b. So I open this bracket. A into 0 is a 0. A into 0 is a 0. I open this and the distributive a of minus b plus a into b. A of minus b into a into b. But I take a b in this side and the left side. Minus ab equal to a of minus b. This is first property and the first part. Similarly, we can put the other way. So other way we can write similarly minus a plus a of b. Instead of 0 we can write minus a of b plus ab. So is equal to 0 is equal. I take this side minus a of b equal to minus ab. This is where I can prove in the similar manner in the proof, simple proof for it. Again the third property minus a into minus b equal to minus of minus a into minus b equal to ab. I take minus a into minus b, I take minus n outside, minus a into minus b, we take one time minus of ab. Minus of ab. I take minus of ab. So we are usually property I was using. So a plus b equal to 0, a equal to minus b. I substituting that. We get that term is a of minus should be equal to plus. We get ab. So third property is for. So similarly we know this distributive property a of b minus c should be equal to, instead of you are using the only two property a of b minus c, we can write a of b plus of minus c. So a b plus a of minus c. So a b. So into I take minus sign outside, a into c. The distributive is over. Similarly, we come to the right distributive b minus c of a equal to b minus, we can take plus minus c, b plus of minus c of a. So b into a plus of minus c into a. So simply say b into a minus c a. Distributive is over. So yeah, you are proving this elementary property only two operations, multiplication and additions. Multiplication and addition. Also of that. This is the first this first sessions for regarding. Using the textbooks or the reference books, Perle, Joseph Galin's